Hello guys, we are group 2 from division G and today we will be talking about instruction pipeline. So first let's see what pipelining is. So pipelining is a speed up technique where multiple instructions are overlapped in execution on a processor.
Now let's see what is an instruction cycle. So in most general cases, the computer needs to process each instruction with the following sequence of steps. The first instruction is fetch instruction, that is, it reads the next expected instruction into a buffer. The second is decode instruction. It determines the code and operates the specifiers. Third is calculate operands. It calculates the effectiveness of each source operand. Fourth is fetch operands. It fetch each operand from the memory and operands in registers need not to be fetched. Fifth is execute instruction. It performs the indicated operation and store the result. And the last is write operand. It stores the result in the memory.
Moving further, let us talk about what exactly is an instruction pipeline and about the segments. Let us assume instruction decoding and address calculation into a single segment, and further, we know that instruction execution and storing of the result can be combined in the next step. Figuring out the assumptions previously mentioned, the instruction pipeline reduces to 4 segments, which includes fetching the instruction from memory. The second one is decoding the instruction. This step or segment also includes calculation of effective address. The third one is fetching operand from memory. And the last step includes executing the instruction. After all these steps are completed, storing the result in proper place is also one of the important actions to be performed. Here we have a descriptive picture depicting the process of instruction pipelining. The figure shows all the 4 segments and their flow, that is, the sequence in which they are present in an instruction pipeline. Pipeline processing appears both in the data flow and in the instruction stream. This leads to the overlapping of fetch and execute the instruction, and hence simultaneous operations are performed. Multiple segments can take different time durations to work on the incoming data. This can avoid the instruction pipeline from working at its maximum speed. Along with this, dealing with the interrupts is also one thing which cannot be ignored. That is, there are occasions when multiple segments request memory access at the very same time. In this case, one segment has to wait unless and until the memory of the other segment is completed. Now, let us understand a bit more about the 4 segments. Segment 1 includes fetching of instruction. This segment can be implemented using the FIFO buffer, that is, first in first out buffer. In segment 2, the fetched instruction is decoded and its effective address is calculated.
In the third case, an operand from memory is fetched in the third segment. We also see that it is a branch instruction. Hence, when it is decoded, fourth instruction is fetched simultaneously. In the final fourth segment, instructions are finally executed in the very last segment of pipeline organization. This is an example for timing instruction pipeline. On x-axis, time is divided in equal stages and 4 segments are represented on y-axis.
Instruction hazards are a type of hazards that occurs when instructions in a pipeline architecture are not executed in the correct order. In a pipeline architecture, instructions are broken down into several stages, and each stage of pipeline is responsible for particular operation. These stages operate on different instructions in pipeline manner, such that one instruction is being executed while another instruction is being fetched and decoded. However, when instructions depend on the results of previous instructions, instructional hazards can occur. For example, if instruction A and instruction B both require the same pipeline stage to execute, then these instructions may need to be executed in the correct order. If instruction B is executed before instruction A completes, then the results of instruction A may not be available to instruction B. There are 3 types of instruction hazards. The first one is structural hazard. Structural hazards occur when multiple instructions require hardware resource. For example, if two instructions require the same arithmetic logic unit, then only one instruction can be executed at a time. This can lead to delays and decreased efficiency in the pipeline.
Next type is data hazards. This occurs when an instruction depends on the result of previous instruction that has not yet completed its execution. There are further three types of data hazards. First is read after write, second write after read, and third write after write. Third type is control hazards. This occurs when there is a change in the order of instruction due to conditional branch instruction. For example, if a branch instruction is encountered in the pipeline, the processor may have discard instructions that are already in the pipeline and fetch new instruction based on the branch conditions. Let's see solution to hazards. First is solution to structural hazard. The structural hazards can be minimized or reduced using hardware technique called renaming. This mechanism states that splits the resource into two different submodules so that we can refer to them separately for different instructions to avoid conflict.
Now let's learn about solution to data hazard. We have two solutions for data hazards. First is forwarding, which is also known as bypassing. The needed data is forwarded as soon as possible to the instruction which depends on it. Second, stalling. The dependent instruction is pushed back for one or more clock cycles. Now let's see some of the solutions to control hazard. Pipeline stall cycles, branch delay slots, branch prediction, indirect branch prediction, return address stack. These are some of the solutions to control hazards.